Alright, welcome back to Meteorology 101. This video, we are going to kick off our series on atmospheric physics 2, and we're going to be covering temperature and moisture advection. Later we get into structure of the atmosphere, formation, dissipation of clouds. So stay tuned for all that, and let's get started. So advection is a horizontal transportation of any substance by the wind. So heat, moisture, it's pretty much what we'll be covering. So when the wind blows, if there's moisture in one area and that wind is blowing the moisture to another area, that is moisture advection. There are 3 steps to determine the magnitude of advection: wind direction and speed, a gradient, which is an indication of wind direction and speed, depending on how tight the isobars are, and we'll cover that in a minute, and the orientation of the isopleths to isobars and contours. So when we talk about isopleths, that is the lines of equal anything. They could be lines of equal moisture. It's just a generic term to cover anything. So when you hear isopleths, think of lines of equal moisture, lines of equal temperature, dew point, and pressure. So contours are height, so isopleths can refer to lines of equal height also. So now the difference is isobars are on the surface. So when you see a surface chart, you're looking at the isobars, surface pressure, lines of equal pressure. When you're looking at the upper air charts, the 850, 700, 500, then you are looking at the contours, the lines of equal height. So it's kind of important to know the difference of that, because the thickness of the atmosphere is what you're looking for in the upper levels. Pressure is what you're looking for on the surface. And advection is an important type of heat and moisture transfer mechanism. And the steps to determine the magnitude, as we just talked about: evaluate the direction and speed of the wind flow. Wind flows parallel to the isobars or contours. More closely spaced isobars or contours, the stronger the pressure contour gradient, and therefore the stronger the wind. So, like I said, isobars are pressure on the surface, contours are height in the upper levels. The tighter those lines are together, lines of equal height or lines of equal pressure, the stronger the wind is. Now, when it says the wind flows parallel to the isobars or contours, for the upper levels, that's mostly true because there's less friction. Once you get above the boundary layer, then there's a lot less friction in the upper levels for the wind. So the wind does travel more parallel with the contours. On the surface, we do have friction because we have the mountains, the trees. Anything that's an obstacle for the wind will slow that wind down, back that wind, and cause friction. So for the most part, they are parallel at the surface, but what you'll find is on a low pressure system, we discussed this in other videos, is wind blows counterclockwise and into a low. So as that wind blows into the low, it creates a low level convergence and then upward vertical motion. High pressure, the winds circulate clockwise and out of the high. So you have a lower level divergence, a downward vertical motion, and that creates a higher pressure on the surface. An example of this is, here's a low pressure system. The isobars, this is a surface chart, and I marked A and B to help determine where we have any type of advection. So when we look at these isopleths, these are isotherms, which are lines of equal temperature, and they are crossing the isobars, the lines of equal pressure. Then we look at the wind speeds, look at those temperatures, and how fast is the colder air blowing into the warmer air, or the warmer air blowing into the colder air. So on point A, you're looking at temperatures When you got warm air to the south, you see the 14, 12, 16, or 10. The warmer air is blown into the colder air, and that is warm air advection. So at point A, you have warm air advection. Point B, we have cold air advection, because if you look at these temperatures, 6, 8, 10, now we have cold air push it to the south with a 25 knot wind. There's a 50 degree temperature, a 56 degree temperature, so you have cold air advection on the west side of the low. So winds rotate counterclockwise around a low pressure system. The tightness of these gradients, these isobars, is the pressure gradient, and that determines how fast these winds will actually go. So if you look at the cold air, see, air moves from high pressure to low pressure. Colder air is more dense, so it moves toward the warmer air and pushes that into a tighter pressure gradient, and you're going to have a faster wind when you have cold air advection. We have the slower winds on the other side of the low, and that's warm air advection. Now, the winds around the low, because of the pressure gradient, is forcing that warmer air up from the south, so it's a lot lighter. The warm air is a lot lighter than cold air, so it takes a little bit more to push that up. So you talk about the magnitudes, you're talking about how tight these gradients are, what's your wind speeds, and how much warm air advection is actually taking place, versus even on the west side of the low, what's the magnitude. We obviously have a higher magnitude here because we have a higher wind speed. We have a more dense air because it's cold, and then the pressure gradient, even though it's not as tight as on the east side of the low, we still have a more dense air coming from the north. So high pressure is pushing into that lower pressure. Step 2 is to evaluate the gradient of the quantity being advected. So we just looked at the gradient, that pressure gradient, and we'll also look at the gradient of the isotherms. How tight are they? So you look at the spacing of the isoplus, the lines of constant values of any given quantity, or look at the values of the plotted stations to determine if there's moisture advection. The term used to describe the gradient is strong, tight, weak, or loose. So we showed you as there's pressure gradient gets further apart, we have a weak wind. Weaker pressure gradient as the spacing is loose. When the pressure gradient gets tighter, then we have a stronger wind speed. So this is still on the surface. We're looking at a tighter thermal gradient. We have temperature of -2, -4, -6. It's all Celsius. And that tight thermal gradient being advected by the pretty strong winds, about 50 knots right there, 65 right there. But there's really not much advection going on here because these isotherms aren't crossing the isobars. So over here is where we have the cold air advection, and then B is just a weak thermal advection. It still would be a cold air advection, but it's very, very weak. So if you look at the how loose these isobars are, then your wind speeds are actually going to slow down. So we get down into a 15 knot wind here versus a 50 to the west over Nebraska. So that's your difference between what you're packing, what the isotherm gradient is versus the isobar gradient. So that changes how much moisture or how much temperature is actually being advected through that system. All right, so step 3 is evaluate the orientation of the isoplus relative to the isobars or contours. The more perpendicular the isoplus are to the contours of isobars, the stronger the advection. If isoplus are parallel to the contours of isobars, then there is no advection. So as they ride parallel, like we talked about, you have weak or no thermal advection or moisture advection, depending on what you're looking for. So as an example of that is A, B, and C. And if you look at A and B, even though A and B we have a 40, 45 knot wind, B is pretty spread out. That's a loose gradient. So you have pretty much no thermal advection. A, you have really no thermal advection because you're still parallel with the isobars, even though you have a tighter pressure gradient. Actually, that's an upper level chart, so that would be a contour gradient. And then to the east on C, you have a tighter contour gradient and a tight thermal gradient, so you have the most warm air advection there because the temperatures are increasing as you go south. So that determines your magnitude, the tightness of both of those gradients, and your wind speeds. And when you get parallel, there's pretty much no thermal advection. The system is pretty much becoming vertically stacked at that point and starting to fill from the bottom up on a low pressure system, and then just starting to weaken. Okay, so significant advection, what makes it significant is the magnitude is based on 3 determinants identified previously. So the pressure gradient, contour gradient, the speed of the wind, and the temperature or moisture amount that's being advected. The gradient, say the temperature gradient. So temperature gradient, pressure gradient, and wind speeds. Significant means there's some effect on the weather. So it's not significant if it's not changing the weather at all. This term is relative to a particular situation being examined. So is it deepening that low? We got warm air advection going into the low, causing that low to deepen, become more intense. Then you can determine, is it making a significant impact on that weather system? Now it is considered significant because it's changing the weather system itself. All right, factors affecting advection: thermal gradient, isotherm spacing. We talked about that. The tighter the spacing, the more thermal gradient. Isotherms most perpendicular to the contours. So we're talking contours, that's upper levels, lines of equal height. So the ones that are most perpendicular, as they become more angled to the contours or more parallel to the contours, then that's when you get the weaker thermal advection, or the weaker advection at all, whether it's thermal or moisture. Greatest wind speeds, the pressure gradient force. So the faster the winds, the more thermal advection you have, or moisture advection you have, the stronger the winds to move that object. And types of advection: we have temperature advection, the transport of air parcels of different temperatures is called temperature or thermal advection. That's your lines of equal temperature being parallel to the isobars on the surface. And then if we got warm air moving into cold air, then that is warm air advection. So warm air advection, air brought into an area previously occupied by cold air. And it doesn't necessarily have to be cold air, it could be just cooler air. So if you got warmer air moving into an area that was cooler, then that is warm air advection. It's just depending on how cold that air was that it's replacing, or how warm that air was that it's replacing. That is where you determine the magnitude, plus your wind speeds, pressure gradient force. Cold air advection is cold air is brought into an area previously occupied by warmer air. So it's just the opposite. The cold air is pushing the hot air out of the way. It's more dense. So then you have cold air advection in that area. Now, we'll get into a little bit of more significance of that, but I do want to cover, say, cold air advection moving into a high pressure system and pushing into that high can cause a higher pressure because it's more dense. When cold air is advecting into a high pressure, it causes that high pressure to become more intense. And then low pressure, if you push warm air into it, that air is less dense, so it will help develop that low and deepen that low, and then cause that to become more intense. So that's the difference between warm air, cold air advection. If you move warm air into the high pressure system, now that it becomes less dense, then your high pressure center is going to drop. The center pressure is going to drop on that system. Evaluating temperature advection. Perform an isotherm analysis on a constant pressure chart. Isotherm are lines of equal pressure. Cold air advection isotherms decrease in magnitude upstream. Lower values are coming toward you. And warm air isotherms increase in magnitude upstream. Higher values are coming toward you. So if we look at this, like this is going to be more of like on a thickness chart. So as the isotherms decrease in magnitude, that just means they're getting further apart. It's a weaker gradient upstream, then lower values are coming toward you. So we have the thermal gradient. You look at point A, a tight thermal gradient. Point B, it's a little bit looser. Both of these, the isotherms are perpendicular to the isobars. So we do have thermal advection. It's just at B, we have cold air advection. If we look at the isotherms, the pressure gradient and the isotherms, we got a tighter pressure gradient at B, a looser pressure gradient at A, but we have a tighter thermal gradient at A and a looser thermal gradient at B. So if we look at the temperatures of those lines, then we have a looser, actual cold air advection at B, with cold air being advected into the warmer air to the south, and then A is warmer air being pushed to the north with a tighter thermal gradient, so we have a greater magnitude of warm air advection. So if you look at the system moving to the northeast is typical steer on a low pressure system. Could move directly east, could push to the south, depending on where a high pressure is basically steering this, or what's steering it in the mid levels. But typically these low pressure systems over the Great Lakes region will push to the northeast. So if you have that strong of a warm air advection at point A, you have a low pressure system pushing into that area where point A is, then you'll likely have an intensification of this low pressure system. Now, if you look at the moisture over the Atlantic, and you do have thermal advection over the Atlantic, so now you have a warm, moist air being pushed on shore, and then that low pressure system being pushed to the east that caused the instability. Now you could look for significant weather all throughout the northeast. So cold air advection, say point A is isotherms colder to the north being pushed south as the wind rotates counterclockwise around the low. B, the tighter thermal gradient. This is the same chart, but we're looking at cold air advection. So we got point A would be where the cold air advection is. It's a weaker cold air advection. So with it being on the backside of that low, which it always is, you're rotating counterclockwise. Unless you have the isotherms just wrapped up around that low and everything's parallel, and then you have a barotropic system, which there's no thermal advection. But in this case, with that thermal advection, you have cold air being pushed around that low, and then there's high pressure obviously behind that. So being a weaker thermal gradient than what we have at B, I would look for this system to deepen or become more intense as a low pressure system. I mean, it's pretty intense right now. This thing is closed. We have several closed isobars, the lines of equal pressure around that low. That's a good indication you have a thermal gradient. You have a pressure gradient, and that low is probably going pretty far up into the upper levels with jet stream support, upper level support, troughing. It pretty much has everything it needs to create whatever weather it wants, but it all depends on that moisture. How much moisture it has. You need moisture, instability, and lift to create the unstable environment to get significant weather. All right, a thickness chart evaluation. Thickness is directly proportional to temperature. Increasing values of thickness upstream from a station indicates warm air advection. Decreasing values of thickness upstream from a station indicates cold air advection. So it's the same thing. What you're looking at is cold air advection being pushed to the south, lower heights with cold air, higher heights with warm air. So as you get the lower heights pushing into the higher heights, then it's going to decrease the heights, and that is a cold air advection increase because you're decreasing the values of thickness. You're increasing the values of thickness when you push warm air into a system. Now that warm air wants to go up and will actually create higher heights in the atmosphere, a more thickness. So on the thickness chart, we're looking at from 1,000 millibars, which is about 364 feet off the ground, to 500 millibars, which is about 18,000 feet off the ground. Then this thickness chart is basically measuring the thickness between those 2 points, just so you can get an idea of how thick the atmosphere is across the United States, just based on that thickness chart. And then you can say you have cold air in this area, warm air in that area, and determine your cold or warm air advection. So a thickness chart example, still the surface pressure. We're still looking at the same system. The thickness is the 500 millibar lines of equal height, the contours. When we're looking at the 540 line, which it says 5,400 on this chart, that purple line, that's your thickness line for your rain and snow line. Right along that line, 540 decameters. Right along that purple line is where you'll have mixed precipitation. If you were to have precipitation fall, because of the height of that atmosphere. So typically you'll have a cold system, lower heights, lower freezing level, and that's going to determine your rain snow. Anything to the north of this 540 line is going to be snow. Anything to the south is going to be rain, and anything on that line is going to be a mixture. That's a real important factor of what most people look at for the thickness chart. Now, another thing to look for, I mean, we're talking about advection. I'm getting a little veered off course here, but the advection, we're not having a lot of advection here. A lot of these contours go parallel with the isobars on the surface, so there's really not a lot of height, advection there until you get over here on the east side where we said from the south. So you can see that higher heights, that ridging off the east coast. Now you have a southerly flow. Surface winds are 20 knots. It'd be a lot more in the upper levels. Now you have onshore flow, moisture, instability. You pretty much have everything you need for significant weather to happen right there along the east coast, just over Jersey, southern state of New York. So that would be the area I'd look for any significant weather, just because of this. Like I said, contours are lines of equal height, but they are directly proportional to the temperature advection. So lines, the isotherms. So you're looking at warm air advection right here, even though you've got a higher, the heights is what's actually showing the advection. So that's another significant part with the thickness chart. And also the jet stream, if you look at the tighter gradient for the heights of the 500 millibar, then you can pretty much place your jet stream on this. Now, if I had to place my jet stream down through West Virginia, going up around that ridge and then back down out of Connecticut area, then I would say this is an occluded low. That means that cold air is catching up with that warm air, and you have a cold occlusion coming out of that low pressure system, because the jet stream's not going to cross the front, the cold front or the warm front. It's going to stay right around that triple point. So when you get that contour shooting out, I would bring in a occlusion wrapped around and then going into a cold front, and then where my warm air advection, the leading edge of that warm air, I would place my warm front. So that's just another tip for the thickness chart. Alright, so moisture advection. We were just talking about thermal advection. Now we're going to go to moisture. So, same principles. Transportation of moisture by the wind. There are two types of moisture advection: moist air advection and dry air advection. So, with moist air advection, Air of higher moisture content replaces dry air previously located in the region, and then air of lower moisture content replaces air of higher moisture content previously located in the region for dry air advection. So, are we pushing dry air where warm areas, where moist air used to be, or moist air where dry air used to be? That's the question. That's what we're looking for to determine: are we adding moisture to the system? We're taking moisture away from the system, and then how does that affect that system? So, evaluating the moisture advection on a surface and 850 chart in the low levels, we use the dew points to evaluate if moisture is spreading into the area. 850 chart, we subtract the dew point depression from the temperature and get the dew point value and evaluate the values upstream. So, subtract the dew point depression on the upper levels, even though I say I'm calling this a low level, surface and 850. 850 is an upper level chart. It's right around 5,000 feet. So still the low levels, but it's off the surface, and then we go to the contours. We're not looking at isobars, we're looking at contours, the lines of equal height. So the temperatures and dew points on the 850 are in Celsius, but there's not dew points on the value around that weather station. It's a dew point depression. So the dew point depression is simply the difference between the air temperature at that level and the dew point temperature at that level. So we'll get to a chart here in just a minute. If you have a dew point depression of 5 or less, then you can consider that significant moisture. Just to point that out, and then let you know what a dew point depression is. So it's just one number, single digits, that not necessarily single digits, but it's the difference between the temperature and the dew point at that level. Higher values upstream indicate moist air advection. So if you have a higher dew point upstream, then you have moisture pushing into the region. Lower values upstream indicate dry air advection. So if you have a lower dew point, then you'll have drier air pushing into the area, so you can determine if are we adding moisture to that system or not. Another method is to draw isodrosotherms, and that's lines of equal dew point. So on the surface, like I said, they don't put isotherms on there, lines of equal temperature. So you have that option if you want to plot the isotherms. You want to plot on lines of equal temperature, or do you want to plot the isodrosotherms, which are lines of equal dew point? So depending on what you were looking for. Are you looking for temperature advection or moisture advection on that surface chart? So the Isodrosotherm Analysis, we still have that same low pressure system, isobars, lines of equal pressure, and then if you look at the solid green lines, now we're looking at in Fahrenheit, the on the surface, the isodrosotherms are lines of equal dew point. So 65, 60, 50, if you push up through there. So now right there in over Connecticut, Jersey area, like we said, with that southerly flow, we're pushing that higher dew points. We're getting down to 60 to the south. We're pushing that to the north. Dew points of 50, 55, and we're pushing more moist air into that area. So now we do have moisture advection. We have warm air advection. Like I said, higher heights with the warm air advection, moisture advection. We have our instability, onshore flow, creating some lift. With the low pressure system, that's pretty much going to cause all the lift you need. There's frontal systems that are pushing through there. And then, so you have all the moisture, instability, and lift you need. So like I said, right off the East Coast right there, I would look southern New York down to Jersey. That's where I would look for the significant weather on this chart. All right, upper level dew point depressions. So as we look up at upper level dew points, like I said, it's not a dew point temperature. So if you look at the station plots, we have a negative 14 over eastern Iowa for that station, and then we have a dew point depression of 3. So we're going to have a minus 17. We're going to add that, the temperature, the difference between the temperature and the dew point is 3 degrees. And the dew point is always colder than the temperature. So we have minus 17 for the dew point. if you look at these black station plots, anything below a 5, they color in black. So now you know you have significant moisture in these areas. So if you took a green marker, you could just circle a cloud right around all that solid, those solid black stations, and then you can see you have a 50 knot wind to a 55 knot wind, and then this moisture being pushed over here into the drier air. So now you have moisture advection pushing into Indiana and into that area. So now it's just quick. It's a quick, easy look for the upper air charts to look at your dew point depressions, anything 5 or less, that's significant moisture, and then where your advection goes from there. So lower values upstream indicate moisture advection. The air is getting closer to saturation, and the higher values upstream indicate drier advection. The air is getting further from saturation. So when you get these higher values of your dew point depressions, so now the air is drier, you're pushing into these moist areas. Now you have drier advection going into that, so you're drying it out. So now you can have, as you watch these clouds on the backside of that low, as the low pressure moves out, you can watch those clouds dissipate with the drier entrainment being pushed into the clouds, and then it just causes them to dissipate because the temperature and dew point spread get too far apart, and then that air spreads out, and then can hold more moisture. So the moisture is no longer saturated. All right, other products available to determine if you have moisture advection: satellite, radar, and the models. So models are just an indicator. It's a tool. It's not for sure. So you have to verify these models, make sure they are initializing well and handling that system well enough to determine if you want to use that as an indication of moisture advection. Radar, if you push radar, reflectivity of the radar into an area and it's raining, you can pretty much say you have moisture advection into an area where it wasn't raining. That's pretty obvious. And the other one is satellite. If you watch this loop, you can watch over Ohio. You watch these clouds dissipate. You watch this clouds pushing into the area, so you have moisture advection at those levels. So we can see our rotation. We're actually looking at the same low pressure system, so we can see our rotation over the Great Lakes region. It's a pretty big system, and then you got that front dropping down off the East Coast. So if you're looking for any significant weather, I would look for it over that northeast where we were showing all that onshore flow, moisture advection, warm air advection. Now if you look at the Great Lakes, you can see definitely got the moisture availability right there. So we're taking moisture off the lakes and pushing moisture into that area also. Okay, and now the atmospheric significance. Forecasting moisture advection within pressure systems can help determine if it will stabilize or destabilize a layer. So when you break all this down, what you're looking for on these upper air charts, that when you're looking at those dew point depressions, the surface chart, you're looking at temperatures, dew points, moisture advection, cold air advection, wind speeds, pressure gradients, thermal gradients, all this, taking all that into account, then you can go to each level and you can determine what kind of advection you have in your area, and then you can put it over top of each other as layers and then determine if you're going to be stable or unstable. So warm over cold is a stable layer. Warm air wants to rise, cold air wants to sink, so there's nothing they're not affecting each other there. That's stabilizing the layer. Cold air advection, the cow is unstable. Good way to remember that is if you ever went cow tipping, cows sleep standing up, and you can actually go out in the middle of the night and knock them over. So it's called cow tipping. So the cow is unstable. That's just a quick way to remember this. So cold air wants to sink, warm air wants to rise. So when you have cold air over warm air, then you just have a lot of mixture going on. Unstable environment. So at the 500 millibar level to the 700 millibar level, if you have cold air advection, and then 700 to 850 you have warm air advection, you have cold over warm, so you have an unstable layer from 500 to 700 all the way down to 850. And then from the surface up to 850 you have cold air advection on the surface, then you have warm over cold from 850, 700 to down to the surface, that layer is actually a stable layer. So now you have a stable layer on the surface, unstable layer on the upper levels. This would be a good indicator, like a subsidence inversion. You could push that air, can push it down and create a higher pressure on the surface and cap it off and create a stable layer with a when temperatures increase with height. That is a stable layer. The atmosphere naturally, temperatures decrease with height. The higher you go, the colder it gets. That's a normal environment we live in. So you're always cold over warm, and we are in an unstable environment. So when you go to the opposite direction, when your temperatures are increasing with height, now you have a stable layer because your warm air is aloft. So the warm air wants to rise, cold air wants to sink, and you're creating a stable layer at that point. Now, if you have a stable layer like that, or a high pressure system on the surface, and cold air has a lower heights because it's more dense and just compacts to the surface, creating higher pressure, then what's happening in the upper levels? Do you have rigid in the upper levels? Do you have an upper level low? Sometimes you can have high pressure just come in, fill the surface low, and then cut that low off from the upper levels, and then that upper level low just sits there. Now you have unstable in the environment in the upper levels, stable in the lower levels, and now you have, if you create any precipitation, then you have that precipitation falling through that high pressure system, and if it's cold enough, has your freezing levels dropped enough, that can be snow, depending on what all that is. If it's 600 to 1200 feet, the freezing levels below 600 feet, or above 1200 feet, whether you're going to have snow, rain, or mix. So we'll get into all that later. You can go to meteorology101.com and pull up articles on that, and that will actually show different charts I have drawn out that show you different freezing level and what types of precipitations you'll have. So this point here is just cold air advection over warm air advection. We have an unstable layer, say like an upper level low. At the surface, we have warm over cold from 850 to the surface. So now we have a stable layer. So now we're looking in any weather to happen in this area would be strictly in the upper levels. I hope you learned something here. If you have any questions, put them in the comments. Visit meteorology101.com for a lot more information. If you have any questions about any of that stuff too, just you can comment here, refer to the article. I'll see what I can get an answer to you, and then hopefully you learned something from this. So stay tuned. We're going to be continuing this series on Physics 2, the atmospheric physics, and go back and watch Atmospheric Physics 1. I got about 5 videos out there, different types of atmospheric physics on Part 1. A little bit more complicated than this. This gets more fun as far as applying it to the charts and actually seeing how that's going to affect that weather system. And as you pull up these charts, you can just start seeing these features. Then, like on the East Coast, where it's pushing up into Jersey and New York, that shows that's where I would look for any significant weather, just by seeing all of these features come together and draw that area. So I want to say thanks for watching. Subscribe to the channel if you haven't, and get your head in the clouds.